In Chem 1A, we said ionic solids are either soluble or insoluble in water. It turns out that when an insoluble ionic solid is placed in water, that solid is in equilibrium with its ions. The equilibrium constant for this reaction is called the Ksp, Sp for solubility product. Let's take a look at this picture. This picture shows ionic solid AB in equilibrium with its ions. Earlier in Chem 1B, we identified the chemical force that determines the solubility of ionic compounds in water. So stop the video and see if you can remember those forces. And the answer is lattice energy, which is energy required to break up the ionic solid into ions, and hydration energy, which is energy released when individual ions are surrounded by an entourage of water molecules. Let's take a look at the equilibrium constant Ksp for 3 ionic compounds. Stop the video and answer this question. And the answer is magnesium hydroxide. This compound has the smallest Ksp, which means it'll have the fewest products in solution. Based on Ksp, magnesium carbonate is the most soluble of the 3 compounds. Let's say we dump 1 mole or 84 grams of magnesium carbonate in 1 liter of water. Applying equilibrium principles, we can answer these 2 questions. How much magnesium carbonate dissolves in water, and what is the magnesium ion concentration? So stop the video, review this calculation, and then you can fill in these boxes here. And the answer is, of the 1 mole or 84 grams of magnesium carbonate dumped in 1 liter of water, only 0.53 grams of magnesium carbonate dissolves in the water. This gives the magnesium ion concentration of 6.3 times 10⁻³ molar, or 0.15 grams of magnesium ion per liter. A look at a solubility rules table will tell us that most carbonated salts, including calcium carbonate, are insoluble in water. What substance could we use to dissolve calcium carbonate? So stop the video and answer these 2 questions. Here are the answers. This equation represents the solubility of calcium carbonate in water. The carbonate part of calcium carbonate is the base. The base reacts with an acid H+. It'll remove the carbonate, which is the product, and that shifts the reaction toward the product side and dissolves calcium carbonate. A solubility rules table will also tell us that most hydroxide salts, including magnesium hydroxide, are insoluble in water. Again, what substance could we use to dissolve magnesium hydroxide? So again, stop the video and answer these 2 questions. And the answer is, this equation is the equation that represents the solubility of magnesium hydroxide in water. Hydroxide is the basic part of magnesium hydroxide. Since it's a base, it will react with acid H+. The H+ removes the OH-, and that shifts the reaction toward the product side and dissolves the magnesium hydroxide. Let's do a practice problem. 1 mole or 58 grams of magnesium hydroxide is dumped in 1 liter of water. Stop the video and do answer these 2 questions. So here are the answers. So this equation shows the equilibrium of magnesium hydroxide with its ions, and Ksp for this reaction is 1.5 times 10⁻11. Here we set up the equilibrium calculation, substitute our equilibrium concentrations into the equilibrium constant expression, and then solve for x. So x turns out to be 1.55 times 10⁻⁴ molar, which is the magnesium ion concentration. And to calculate the pH of the solution, we need to know the hydroxide ion concentration. Based on hydroxide ion concentration, we calculate the pOH, and then finally the pH. Earlier we said that adding an acid to an insoluble hydroxide should dissolve that insoluble compound. So stop the video and answer this question. So the answer is big K, and we can actually calculate a numerical value of K by looking at these 2 equations. First, we need to know this. If we have reaction A plus B going to C, and the equilibrium constant is K1, and we have a second equation, C going to D, the equilibrium constant is K2. Add those 2 equations together, we get A plus B going to D. K3 is equal to K1 times K2. Let's apply that to these 2 equations. We looked at the equilibrium constant for this reaction earlier. That's called Ksp. The reverse of this reaction is the dissociation of water, Kw. We multiply that reaction by a factor of 2, therefore we have to square the equilibrium constant. Adding the two equations together gives us this equation, and our equilibrium constant for this reaction is 1.5 times 10 to the 17th, a very large equilibrium constant, which tells us that this reaction occurs. Salinas has hard water, which means that our water has a lot of calcium ion and magnesium ion in it. Hard water causes lime stains on our utensils and fixtures, also requires more soap for cleaning, and then leaves clothes a dingy white color after washing. So stop the video and answer this question. So here's the answer. When water passes over limestone rocks, some of the calcium will dissolve in the water. So let's apply our knowledge of chemistry. So what chemical could you use to get rid of soap scum, these red-brown iron stains in your bathtub, or grease? Stop the video and think about that for a minute. Here are the answers. So if you happen to see some of those stains at home, use vinegar to get rid of those stains. Kitchen grease is a fatty acid, so you got to use a base such as TSP or sodium phosphate. Motor grease is a nonpolar substance, so use a nonpolar solvent such as gasoline to get rid of the grease. When aluminum ions and hydroxide ions are present in water, aluminum hydroxide soluble form. Aluminum hydroxide is an insoluble hydroxide, so it can be dissolved by adding acid. Another way to dissolve aluminum hydroxide is by adding a base. That'll form the soluble complex ion. The third reaction shows the formation of the aluminum hydroxide complex ion. We can look up the equilibrium constant for compounds that form complex ions. Note, each of these reactions has a large equilibrium constant. Gold and silver are mined by forming complex metal cyanide ions. So the metal is first oxidized to an ion, then the metal is combined with cyanide to form a complex ion. The complex metal ion solutions are collected, and then the metal ions are reduced to get the metal back. Another way to extract metals from the earth is biomining, in which microbes eat metals. Biomining is an environmental friendly technique compared to typical mining.